All right, now let's restart this. All right, 8A. What mass of K2O? How do we name K2O again? From our nomenclature practice. Potassium oxide. That is it. K2O in grams is produced when 25 grams potassium is reacted with 20 grams of calcium oxide via the chemical reaction below. All right. What do we think is step number 1? Balance it out. So how do we do that? Or I guess like what's the answer to the balance equation? 2 in front of the K. All right. So we're gonna put a 2 here. And is that it? Is it balanced now? Those look balanced to me. All right. So first step, right? Balance the equation. What's the second step? Yeah, we got to figure out what the limiting reactant is. And there's a whole series of steps on how to do that. What's the first one? So we have grams here, right? What should we do with the grams? Convert to moles. So moles of, yeah, we'll just convert the grams to the moles of stuff. So 25 grams of potassium. And how do we get from grams to moles? By the molar mass. So if we look at the molar mass here of potassium, it is going to be, I'm going to round that here to 39. So 39 grams of potassium in 1 mole. And let's go ahead and do the same thing for our calcium oxide. So 20 grams of calcium oxide. What's the molar mass for calcium oxide? Yeah, and what's that equal to? 56. 56 grams for every 1 mole. So, I'm gonna hold off, right, on doing anything else with these numbers. So we have our answer in moles now, right? So what do we want to do next? Yeah, the mole to mole ratio. What do we want to, or yeah. So basically what I'm trying to get at is what you do basically is figure out your mole to mole ratio and convert it into the moles of the product that you want. Because, right, if you were to compare the moles of potassium and the moles of calcium oxide, it would be like comparing apples and oranges. Like you can't really do that. So first I try to get them down into the same thing, the moles of the product that I want. Then I can see, okay, this one's lesser than that one. So, all right. For that, we're going to do this. For every 2 moles potassium, there's 1 mole of K2O. And again, I got that by using mole ratio. We're going to do the same thing here, but this time the mole ratio is just 1 to 1. So for every 1 mole of calcium oxide, there's 1 mole of K2O. You don't have to put these ones here if it's a 1 to 1 ratio, because 1 divided by 1 is 1, and anything times 1 is itself. So a little bit of math. All right. What do we get when we solve these two things? Zero 0.32. All right. So we have 0.32 moles of K2O. And what about for the next one? 0.36 moles of K2O. All right, we have 0.32 moles and 0.36 moles. So which of these is our limiting reactant? So the limiting reactant is the one that limits the amount of product we make. So the one with the less amount of moles is going to be our limiting reactant. Whichever one produced the less amount of moles. Potassium. Potassium is our limiting reactant. So what I'm going to do here is get rid of all this stuff because we don't need it anymore. So we found out that potassium is our limiting reagent. So I'll just write that to the side here. K equals limiting reagent, or I abbreviated that to LR. So are we done? That's it? No, right? Because it says what is the mass of K2O in grams. It's always important to read the question. So 0.32, right, moles of K2O. How do we get from moles to grams again? Times molar mass. So 1 mole is how many grams? What's the molar mass here? $94. Yeah, sounds about right. 94 grams of K2O. All right. Now, what do we get when we solve this out? 30.1. Say that again, sorry? 30.1. 30.1. So 30.1 grams of K2O. All right. We have to take into account our sig figs. Is this the correct amount of significant figures for this problem? Why not?
Because the two numbers they gave us are only have two. Well, actually, the lowest one really only has one.
Right. So you have to go to the lowest number of significant figures, which in this case, as gentleman in the front pointed out, is in fact 20. So 20 only has one sig fig, so we only have to go to one sig fig. So 30.1 rounded to what? To one sig fig is what?
30.
Just 30, yeah. So this would be 30 grams of K2O. All right. And that is that for part A. Any questions over that? All right. Let's move on to part B. A Gen Chem 1 student successfully performs the experiment above and collects 23 grams of K2O products. What was the percent yield of the reaction? Percent yield. It's kind of a weird thing. So how do I calculate this percent yield?
Divide the grams given, but divided by the grams that we found out.
What's another way to say that? Yeah. So percent yield is going to be equal to your actual yield. So the amount of grams you actually got divided by your theoretical yield. So how many grams you could produce 100% of the time if the world was great and life was good. So what is our actual yield in this instance?
23.
23. Or you don't need the G here because they're both the same thing, but same deal. So what's our theoretical yield? 30 grams, yeah. 23 divided by 30, and then this is all multiplied by 100%, right? Because it's a percent. So, all right, what is our percent yield going to be? 73%. All right. Sig fig wise, do we care?
No, 76.
76? All right. 76%. All right. Sig fig wise, do we care at all? All right, we got a couple no's. All right, raise your hand for yeses. Yes, we do care about sig figs. Raise your hand for no, we do not care about sig figs. I with pride. Right. The actual thing is, as a matter of fact, that for this answer, we got to introspect a little bit. Look at your theoretical yield. Is it exact? It's not, right? Because we rounded it off in a few, or the problem prior. Is our actual yield exact? Yeah, right, because they didn't specify. A common thing for these, right, is don't assume it's exact unless they say otherwise. Or if you know you can like count it specifically. Like I have 5 fingers on my hand. Like I can count those up, right? Like 1, 2, 3, 4, 5. Like 5 fingers. Like if you can count it up and you know like with certainty it's exact, then and only then it's exact. So the common thing, right, for this exam, if there's units behind something, it is considered exact. So like something like 1,000 atoms, even though you can't count them up, you still know that there are 1,000 atoms there. Exactly 1,000, not 999, not 1,001. So the 1,000 in this instance is exact. So to the final thing of what I'm trying to get to here is sig figs. Yes, we actually do care about them. So in this case, how many sig figs do we need to have in our answer? 1, right? Because of the 30. So if we were to do that, then what's 76 rounded to 1 sig fig? 80, right? Or yeah, you could say 80, 8 times 10 to the first power, same deal. So this is approximately 80%, taking into account the rules of sig figs. All right. Any questions on that? That was percent yield and limiting reactants all lumped into one thing. Yeah.
So how do we know if and when different apply to the percent? Is that circumstantial or is it?
Well, normally it is, right, every single time, but you have to take into account like which units you used that were exact and which weren't. So say for example, right, this one, we know it wasn't exact because of the problem before. So because of that, we determined that the answer was 1 sig fig. And then here, the 23 grams, they didn't specify that this was an exact number, so that's why we didn't, or we assumed the sig figs for that too. General rule of thumb I let's follow is never say it's exact unless you know for a fact it's exact, like it has units that you can measure and count, like to the nearest integer most of the time. And what's it called? It specifies that it is exact.
Yeah, for this one, it's a 2-part question, right? So you're not gonna have anything like that on the exam. You're gonna have individual questions. This one's a little different because it requires you to use an answer from the previous part in the second part, so you have to take into account that. But typically, it'll be one problem. You look at the numbers in that problem, and it'll tell you how many sig figs in your answer. Does that make sense?
Yeah, and as we covered last time, I just want to stress it again. The only conversion factor that is exact is your 1 inch equals 2.54 centimeters.
You have more limiting reagent problems if y'all want to do more. Yeah. Okay. So this one, if 50 grams of copper chloride reacts with 20 grams of sodium nitrate, how much sodium chloride can be formed? So we know we're gonna have to take into account sig figs at the end. So why not just let's get it over with now so we have an idea later. So how many sig figs should we have in our final answer before it gets too messy? 1 sig fig, right? Because 15 has 2, the 20 with no decimal point has 1 sig fig. Therefore, we should only have 1 sig fig in our answer. So we'll just put that off to the side. All right. What's the next thing you would want to check?
It's balanced.
Is the equation balanced? Is the second question we're asking. So, is this equation balanced? Yeah, so this worksheet gave it to us as a balanced chemical equation. And sometimes on the test, it'll be balanced for you. Sometimes it won't be balanced for you. And they won't tell you. But other times they're nice and they say this equation is unbalanced right next to it. So that means you have to put some coefficients in there so that it's balanced. All right, and then what's the next thing we have to do now that we established this equation is balanced? So it's asking for how much sodium chloride can be formed, and it also gives us information for the mass of each reactant. So I want you all to ingrain this in your mind. If you get information about more than one reactant, you need to automatically think about limiting reagents. Okay, so whether it's 3 reactants in a chemical equation, or if it's 2, if they give you more than one mass for the reactants, then you need to think immediately about limiting reactant. Okay, so I always tell the students every semester, even in exam 2 and exam 3, there's going to be limiting reactants, even though it might be in exam 1 or foundation exam concept. Okay.
Yeah, that's true. I literally missed the limiting reactant question on exam 2. So, yeah, if you don't believe him, take my word for it.
Exactly. So they give us the mass of copper 2 chloride. They give us the mass of sodium nitrate. So that's 2 things. We know we have to calculate limiting reactant. Next, what do we do? What do we do? Convert them to moles, right? So we're going to convert each reactant in that's given to us in grams. We're going to convert that to moles using the molar mass. Yeah, got it? That's how we get from grams to moles. All right, so can someone tell me the molar mass of copper 2 chloride? 134.5. 134.5. And remember, this is stuff you are going to get from the periodic table, so he didn't just memorize that. And maybe he did, and that's pretty cool. So that's for every mole of CuCl2. So this is getting us to moles, because in chemistry we work with moles, because we can convert to anything we need using moles. Next, what do we use? Molar ratio, because we don't care about how many moles of reactant we have. We care about how many moles or what mass of sodium chloride we're going to produce from this reaction, because that's what the question's asking for. Do y'all agree on that? Yeah, okay. So the molar ratio is found from the balanced chemical equation, and we see that for every, here's the laser. So for every 1 mole of copper 2 chloride, there is 2 moles of sodium chloride produced. So that's our mole ratio. So 1 mole of CuCl2 produces 2 moles of sodium chloride. And next, what do we need to do? So we're right now our units are moles of sodium chloride, because we can cancel everything else out. Grams of copper 2 chloride cancels out. Moles of copper 2 chloride cancels out. Yeah, so we're going to go from moles of sodium chloride to mass of sodium chloride, because that makes sense. The question is asking us how much sodium chloride can be formed. So we need to get to mass of sodium chloride. Does that make sense? If there's any questions, ask them now before I keep making anyone more confused. Okay, no questions. So the mass of sodium chloride is 23 plus 35.45. What's that, Rich?
23, 35.45,
58.45.
something like that.
All right, 58.45. Correct me if I'm wrong. For every 1 mole of sodium chloride. So that cancels that unit, right? So now we're left with grams of sodium chloride, and that's exactly what we need, because that question is saying how many grams of sodium chloride can we form. So someone put that in the calculator.
$13.035.
13.056, you said?
035.
0.0356. grams of sodium chloride. Are we done? No, because we only calculated the theoretical yield if we use all of the copper to chloride. So we're gonna do the same thing for the second reactant, sodium nitrate. But is it okay if I go a little bit faster now? I just wanted to get to that first one for, and then I'll finish the second part. So 20 grams of sodium nitrate. Molar mass of sodium nitrate. Can someone get that for me?
85.
85 grams, thank you. And we see that the molar ratio for that is 2 to 2, so it's a 1-to-1 ratio, right? So for every 2 moles of NaNO3, sodium nitrate, 2 moles of sodium chloride are produced. And we know from calculating it earlier that the molar mass of sodium chloride is 58.45 grams. And if we put that into our calculator, what do we get? Also good to see that the units cancel out. To write your units. It'll make sure you're going in the right direction. I'm gonna 13.75, thank you. 13.75 grams of sodium chloride is produced if you use all the grams of sodium nitrate that was given. So now what we have to do is compare the two theoretical yields, and we're looking for which one is the most or the least. The least, right? Because that's going to tell us that the reagent that it came from is the limiting reagent or limiting reactant. Does that make sense? Nod if it makes sense. Good. Okay. Awesome. So which one's the limiting reactant? Copper chloride or copper 2 chloride, right? So CuCl 2 is going to be our limiting reagent because it produced the least amount of sodium chloride of the two, right? So what I'd like to do now is just cross out the one that we don't need anymore. This one, we don't need it. On a test, I would cross it out so I don't get mixed up. Cross out the answer too. Any questions so far before we keep going?
Why is the molar ratio for the first one to 1?
2 to 1?
Yeah.
Yeah, so we're starting with units of grams of copper chloride, and we convert that using the molar mass to moles of copper chloride, right? And we know that from the balanced chemical equation, we see there's not a 1 here, but it's implied that for every 1 mole of copper chloride or copper 2 chloride, it produces 2 moles of sodium chloride. So it's a ratio of 1 to 2. So, and that's what we wrote here. For every 1 mole of copper 2 chloride that is reacted, it requires 2 moles, or it produces 2 moles of sodium chloride. Does that make sense? Got it. Good question. All right. So we already did the part C. Okay. No, we did not actually, because we calculated the mass of sodium chloride, not copper 2 nitrate. So how would we do that?
Grams times moles.
So where would we start? Where would we start?
Molar mass times moles.
Yeah, that's one way. So someone want to kind of walk through where we would go?
Use the same equations, but it is the sodium chloride for the copper 2 nitrate.
Yeah, exactly. So we can start with we know that copper chloride is our limiting reagent. So we're gonna start with our 15 grams of CuCl2. And we're gonna convert that to moles of copper 2 chloride. And then instead of converting it to moles of sodium chloride, we're gonna convert it to moles of copper 2 nitrate. Good job. 134 grams for 1 mole CuCl2. And like we said, the difference here is that we're using the molar ratio of copper 2 chloride to copper 2 nitrate instead of copper 2 chloride to sodium chloride. That's the difference that we're doing here. And we're doing that because it's asking about copper 2 nitrate instead. It's a 1-to-1 ratio. And then someone have the mass of copper 2 nitrate.
$125.45.
Thank you. And what does that give us as an answer?
I know that's wrong, sorry. How we did with that trade? 134. Yeah.
134. No, you're good. You're good. You are good. 134. And did someone put that in the calculator? 14.944. And so I kind of forgot to do sig figs on the first one around, even though I said, let's not forget about sig figs and let's do it first. So how many, we said 1 sig fig. So this number here should have been rounded to what? 15. That would be 2 sig figs. 10, yeah. So 10 grams. In real life, we're not gonna take off 3 grams for something like that. But we are right now because we care about sig. Unless you're an analytical chemist, you really don't care. All right, and same thing with this other one down here, right? Dang, it's really knocking down these numbers. You know what, for the sake of let's not round. It looks like they don't want us to. But let's not take into account sig figs, because if we do that, look at what happens with part D. You end up with over 100% yield if you take into account 1 sig fig. So we're just gonna leave it with the 13 grams instead. But on the test, sig figs, okay? Got it? Okay. So yeah, we're not gonna do that this time. Okay. So you said 14.944. Let's just round that to 14.94 grams. And last thing is if 11.3 grams of sodium chloride are actually formed in the reaction described in problem 1, what is the percent yield of this reaction? So Rish was telling you earlier that the equation for percent yield without looking at your notes again is what? Yeah, actual over theoretical times 100. So I just abbreviate this A over T times 100 equals percent yield. Y'all can read that. All right, so we actually produced how much? 11.3. And we thought we were going to produce how much? Say it loud with your chest. Yeah, 13.0. Let's round that to 0.4. All right. So 13.04 grams. And we're going to multiply that by 100. Is this a good, well, do the math. So let's see if this chemist did a good job or not. 87%. That's pretty good. Although you can just buy sodium chloride at the store. You don't need to do all this. All right. Is there any questions on any of this? I know it's a lot of stuff, a lot of steps you got to think about, but with repetition, doing this over and over and over and over again until it gets so bored or so boring to you that I don't know, you wanna text your ex or something, then you're gonna do the, then, yeah, you know what I mean. Just keep doing it until you're so bored. Don't tell my girlfriend that's it. I'm not gonna text. Okay. Another one, or y'all wanna do something, a different type of problem? Different, how do y'all feel about ionic equation? Net ionic equation? You do some? Okay. So the one important thing that you have to remember for net ionic equations is solubility rules. So I hope you all remember your solubility rules. How many of you remember your solubility rules?
I think y'all were given them, right, in basic chem, from my understanding. But unfortunately, for this class, you have to commit them to memory.
Are they on the MCAT too?
Yeah, we got some questions.
Yeah, so if you're up taking the MCAT, you gotta know some solubility rules. That's okay. All right, let's do all right, let's just do number 6. All right. So not only do you need to know solubility rules, you also need to know what kind of reactions are taking place, so that way you can predict their products. So right now, we're given us 2 salts, and what kind of reactions do salts typically undergo? We have combustion reaction, single displacement reaction, double displacement reaction. Did y'all learn about these in basic? Okay. So did you say it? Double displacement, right? Because I'm gonna highlight them. We know the one in the front is the cation, it's the positive one. We know the one in the back is the anion. So they swap. The cation of one swaps with the cation of the other to pair up with its anion, and then vice versa. So what would be our first product? We're swapping them, remember. So potassium is going to go with nitrate. So what would that product be? KNO3. Because potassium has a +1 charge, nitrate has a -1 charge, so they combine to just make KNO3. No parentheses or anything. What about aluminum and phosphate? AlPO4. And again, these are what's it called? Aluminum has a +3 charge, phosphate has a -3 charge, so they cancel out. So it's no parentheses needed. It's AlPO4, like Abby's. Okay. What's next? Balance. We definitely want to balance. Can someone tell me what the how balance is? You can do it on your paper. That's what I was thinking. A 3 in front of the potassium nitrate would make this equation balanced, because we have 3 potassiums over here. We have 3 nitrates over here. We only have 1 phosphate and 1 aluminum on this side, so this is good. This is the only thing that we have to change. All right, what's next? Split them, yeah. But how do we know what to split and what not to split? Because remember, you can only split things that are in the aqueous phase. This is where that solubility rules comes in. Is potassium nitrate soluble? I got one person shaking their head no, one person saying yes. Anyone else want to be a tiebreaker? Maybe throw out a guess. Yes, so potassium is a group 1 metal. We know that group 1 metals form salts that are always soluble. Always. It doesn't matter if it's with the most insoluble anion, group 1 metals are always going to have soluble salts. And also nitrate also forms soluble salts all the time. So KNO3 is like ultra soluble because you got soluble on potassium's end, and nitrate is also very soluble when it's in salt. So KNO3 is aqueous. What about aluminum phosphate? I saw one person shake their head, but they're not confident, so maybe they are confident. You think it's solid, and why? What would make you think that? Aluminum. What are the solubility rules for aluminum? Yeah, so I don't really know aluminum solubility rules, but I do know phosphate solubility rules. Phosphates are generally insoluble, except when they're paired with group 1 metals and a couple group 2 metals and ammonium. And aluminum is not one of those, so this is going to be a solid. So now that we know what is aqueous and what's solid, we know what to break in a solution into its ions and what not to break in a solution. So I'm just going to start over here. So I'm going to start, we have K plus, because potassium phosphate's soluble, and 1 PO4. Are y'all with me so far? Yeah, no, I got a no. Where did I lose you?
Yeah, I don't know.
Okay, yeah. So there's not much I can do except say memorize them. You'll have a chance to redeem yourself for sure after exam 1, because you're tested on solubility rules again. You can also try to memorize them, today, tomorrow, and the day of the test. But it's all just memorization. I don't know like any shortcuts to that. But if it was more a conceptual thing, I would be able to help you with that. Is there anything that might not make sense conceptually?
So you just knew it was a solid? No.
Which one? Aluminum phosphate? Yeah. I knew it because solubility rules told me that I memorized. Yeah, so that'll be a big thing to remember for this upcoming test in exam 1 after the foundation exam.
I don't know, over the next couple of days, make the solubility rules your lock screen or something. And just stare at it in the dark, alone, crying in a corner.
Sounds like you have some experience. So we're breaking everything that's aqueous, and we know it's aqueous again because of solubility rules. So 3K plus aqueous plus 3NO3 minus. And then we have aluminum phosphate, which is a solid in solution. It's not soluble, so it's going to stay a solid in solution. So I'm sorry, I kind of ran out of space. I think y'all get the gist. Yeah. And now this is the fun part. I guess you could say you're just canceling everything out that's the same on both sides. So for example, we have 3K plus aqueous on the left. We have 3 potassium ions, or K plus aqueous on the right. We can cancel those out. And what else can we cancel out? Yeah, so we have 3 nitrates on the left, 3 nitrates on the right. And so our net ionic equation is everything that didn't cancel out. So aluminum 3 plus aqueous plus 1 phosphate Produces aluminum phosphate precipitate. This is also called a precipitation reaction. It produces a precipitate. So this would be your net ionic equation. You might be asked to do your total ionic equation. That's just the one that we initially did before we canceled anything out. So that's a total ionic equation because it has all the ions that were involved. And then your net ionic is everything that after you canceled everything out. That makes sense? Yeah.
Let's scroll down for 1 second. On this PDF, conveniently placed are solubility rules. So take a picture of them, memorize them. Yeah.
Can you post this video from last time?
The video? The recording?
The actual,
The document?
yeah.
Yeah, sure. I'll send it into the group me. Are you in the group me? Yeah, so memorize these. If you haven't, there's still plenty of time. Just make some mnemonics and you can get them. Yeah, solidified in your head pretty quickly. What kind of questions do you want me to do next? You got 10 minutes. Yeah.
You find like 2 percentages, but they give you which one of them.
Yeah, you can bring the picture. Okay, that would be. Everyone got their pictures? Okay. Yeah, if you could leave it, that would be really helpful. Give you my chair. If anyone has another question, I'll be walking around. If you have questions you didn't want to ask in front of everyone.
All right. So if y'all didn't hear, her question was basically how to find the relative abundance or the percent abundance of 2 different isotopes. They give you 1 percentage, but you need to know the other one or the other 2. So here's the question, right? Molybdenum has a relative atomic mass of 95.95 AMU. So 95.95 AMU, that is the total atomic mass. And it gives us this information. So it says molybdenum 92, this isotope has an abundance of 1.15%. This 95 molybdenum has a mass percentage of we don't know yet. And same with this 98 molybdenum. So basically, what we're tasked to do is find the percentages of the 95 molybdenum and the 98. All right. What is AMU? Like how do you find it? How do you find it in the first place? Periodic table, but what is it in relation to isotopes?
The average mass, or the weighted average.
Yeah. That's the correct terminology. The weighted average of all of an element's isotopes. So basically, a weighted average is just a fancy way of saying the average, but each thing is worth a different percent. Like it's basically like your classes, right? Like quizzes are worth 20%, tests are worth like 60%, stuff like that. Isotopes follow the same thing. So now it's a weighted average, right? So basically what we have to do is now we got to find out our percentages. So our weighted average, what I'm going to do is set up an equation. So 1.15 as a percent is kind of difficult to work with. So I'm going to convert it into a decimal. So to do that, I'm going to move this basically 2 decimal places to the right, 2 points to the right, and I get 0.0115. Then I'm going to multiply that by the atomic mass of our isotope here, which is 92. Again, this is just a weighted average. This is generally what it looks like. So I'm going to do the same thing for the other two. So we don't know what the percent abundance is, right, of the 95 isotope. So let's call that X, because we don't know what it is. So X, and then we're going to multiply this one by 95. And then once we do that, we're going to add this again. So 98, and then we don't know this percent abundance either, but we can call it Y. All right, y'all with me so far? Y'all on the same page? All right.
So he didn't give you like the equation with the variables, but what he's doing is the equation you have to use for these types of problems is that the average mass is equal to the percentage of the first isotope in its mass plus the second percent abundance times mass of the second isotope and so on. So if you have three isotopes, you'll do it 3 different times, 1, 2, 3, and so on. So that's the equation he's using.
Yeah, that's what the average mass is equal to. So that's why I said this all equal to 95.95. As that is the average mass we were getting. All right. What do we know about all of our percentages? What do they have to add up to? 100, right? 100%, because it's impossible to have more than what you were given, I guess. So we know that X, as that's a percentage, plus Y, another percentage, plus 1.15 equals 100. Or you could change this into the decimal form if you want. So yeah. All right, let's clean this up. Let's clean up these equations, make them nice and pretty to look at. So we have here, or I should probably change this into a decimal to keep everything consistent. So X plus Y plus 0.0115 equals, instead of 100%, it's just 1, as that's 100% of the decimal. All right, now let's clean everything up, make it look all nice and fancy. So let's clean up the bottom equation, the one in teal, as that's easier. So X plus Y, and then what do we do to this 0.0115? We want to get the variables by themselves, so subtract it. So what do we get when we do that? Minus 0.0115. .988. All right, so this is one of our equations. So let's keep that aside. Now let's clean up the one in green. So we need to get the variables on one side again. So we have 0.0115 times 92. So when we multiply that out, what do we get?
Zero.
1.05. And of course, we gotta subtract this over to the other side because we're trying to get all the variables to one side of the equation. So what do we get when we subtract 1.058 from both sides? And cross this out right. 94.892. All right. Now let's combine both of our equations. So what we have so far is 95x plus 98y equals 94.98, or sorry, 892. And then we have on the bottom here, x plus y equals 0.988. Now y'all are probably y'all probably have some PTSD from algebra class, but that's what we have to do here to solve this problem. If you remember, there's two ways to solve these. They're called systems of equations. You can solve them by substitution or by elimination. Which one do you want? Elimination. So how do you, or what do you want to multiply by? Or in which equation do you want to multiply it into?
And it is 95 to 100.
Yeah, negative 95 to the bottom equation. So she wants to solve for y first, which is fine. You can do either. Solve for x or y, nobody cares. You have to solve for both of them anyway. So we're going to multiply the bottom equation by negative 95. When we do that, we get negative 95x minus 95y equals, what's 0.988 times 90 or times negative 95?
Negative 93.86.
So 93.86.
Yeah.
Negative 93.86. Negative 93. Yeah, that's fine. All right. So what do we do now?
Add those. Got it.
Yeah, you add them up. So, and once we add them up, we're gonna combine both equations. So 95 and negative 95 are gonna cancel out. So we get 98y minus 95y, which is just 3y. So 3y equals, what's the right side of my equal sign equal to? We're subtracting 93.86 from 94.892.
Do three, two.
1.032. All right. Now,
Go back
all,
here.
also left, yes, divide both sides by 3. And what is y going to be equal to?
0.341.
0.34. And remember, this is a decimal, so we have to convert it into a percentage. So if we multiply this by 100, we get 34.4%. So that's one of our percentages. All right. So we have something that's 34%. We have something else that's 1.15%. So now, which equation do y'all want to use to solve for this remaining percentage?
X plus one.
Yeah, the x plus y one. So we're gonna plug in our decimal number again because that's what I decided to use for whatever stupid reason. So x plus 0.344 equals 0.988. So what is x?
0.644.
0.644. X is gonna equal 0.644 or 64.4%. All right, now we have all of our abundances. So the 95 molybdenum one, the abundance is 64.4%. And the other one, the 98 molybdenum, the abundance is 34.4%. All right. So we've done all of that math, right? So now there's one last and final thing we need to do. We have to add them all up and see if they equal 100%, because that's the way we can truly determine if we did it correct. So if we add all of these percent abundances up, do we get 100% or something close to 100%?
That's
What do we get?
99.95.
99.95, which I don't know about you, but that's pretty close to 100% for me. So, and the reason why we didn't get 100% exactly right is because we might have rounded somewhere in the middle. So it's safe to assume that 100% is the correct answer. So All in all, that's how you solve these questions. That's how you get, two percentages, 2% abundances when you're only given one. It's just a lot of weird math and weird algebra. And, I have a strong suspicion, right, just, me personally, strong suspicion that this is something that you need to pay attention to in your study. Now we all know how to do it. So any questions on that?
Yeah, you also really know how to do this.
There may, even if they're like 3 percentages, it's the same thing. You just add another variable.
So make sure you know how to do this, because something's telling me y'all might need to know how. Something telling you, Rich?
Yeah, I've got a strong feeling.
Yeah. So, yeah. If you need more practice, I'm sure you can look on YouTube for more practice problems where someone works it out. And they'll just type in percent abundance problems with 2 missing percents or something. I'm sure you could find it pretty easily if you want to make sure that you know how to do it for the test that you might see it on. Okay.
So that's good.
This exact problem with Rich's work. No, we can do that. But I mean, can you read it?
What is it? Boy, my handwriting again. You thought I wrote neat this time. All right, yeah, I'll take a picture of it and send it in.
But yeah, if you have any other questions, like just you want to be answered really quickly, you can come up here. We'll be here for a couple more minutes.